Powering civilization with nuclear energy requires a massive, hyper-specialized industrial supply chain. These complexes solve a single, microscopic problem hidden inside raw uranium ore. When you pull natural uranium out of the ground, almost all of it, 99.3%, is an isotope called uranium-238. It's incredibly stable, which also makes it useless for generating power. The actual fuel you need to sustain a fission chain reaction is uranium-235, and it makes up less than 1% of the mined material. Isolating that tiny fraction is a colossal engineering challenge. Because U-238 and U-235 are isotopes of the same element, they are chemically identical. You cannot separate them by burning, melting, or using chemical solvents. They react to everything in the exact same way. There is only one physical difference engineers can exploit. The useless U-238 atom has 3 extra neutrons, making it exactly 1% heavier than U-235. But natural uranium is a dense, solid metal. Trying to separate two perfectly mixed metals based on a 1% weight difference is physically impossible. To even attempt it, you have to radically change the material's state of matter. The process starts by milling the raw extracted ore into a concentrated solid powder known as yellow cake. At a conversion facility, this powder is reacted with fluorine to create a new compound called uranium hexafluoride, or UF6. The advantage of UF6 is its volatility. Heat it to just 56.4 degrees Celsius, and it sublimates directly from a solid into a gas. But turning uranium into a gas introduces severe environmental risks. UF6 is highly reactive, particularly if it comes into contact with the slightest bit of moisture in the air. If a leak occurs, the gas immediately decomposes, reacting with the ambient humidity to form hydrochloric acid and a highly toxic compound called uranyl fluoride. Visually, this creates a dense, corrosive gray-white fog that can severely burn lungs and skin. To make that 1% weight difference exploitable, engineers turned a stable solid into a gas, but they created one of the most toxic, difficult-to-handle industrial substances in the nuclear supply chain. To actually separate the isotopes inside that gas, facilities use a machine called a gas centrifuge. The UF6 is fed into a tall, cylindrical rotor designed to spin at extreme speeds. This is where the weight difference finally matters. As the cylinder spins, centrifugal force acts on the gas. The slightly heavier U-238 molecules are thrown outward against the cylinder wall. Meanwhile, the lighter U-235 molecules don't get pushed quite as far. They stay clustered in a column closer to the dead center of the spinning cylinder. Internal scoops then carefully siphon off this central U-235-rich stream as the enriched product. The material pooled at the outer wall is scraped away and discarded as a depleted tail. The physics work perfectly, but the output of a single centrifuge is microscopic. By itself, one spinning rotor barely makes a dent in the enrichment required to actually build a functioning reactor fuel rod. To build up a usable concentration, the slightly enriched output from the first centrifuge is piped directly into a second machine, where the process repeats. The depleted tail is piped pipewards to be reprocessed. This networked loop is called a cascade. Commercial enrichment plants connect thousands of these centrifuges together, creating a vast, highly synchronized labyrinth that continuously refines the gas step by step. For a civilian power plant, the operational endpoint is known as low-enriched uranium, or LEU. The cascade keeps looping the gas until the U-235 concentration rises from that natural 0.7% up to somewhere between 3 and 5%. Once it hits that target, the enriched UF6 gas is piped into large transport cylinders. It is cooled for about 5 days until it safely transitions back into a solid for shipment to a fuel fabrication plant. This interconnected network extracts vital energy from raw earth. But the sheer efficiency of the cascade creates a severe, inherent global security threat. This chart shows the effort required to enrich uranium, measured in separative work units. Notice the steep vertical climb on the left side. Getting natural uranium to the 5% civilian power level takes massive energy, time, and effort. But look at the rest of the graph. Once a facility reaches around 20% enrichment, the curve flattens out. Jumping the rest of the way to the 90% purity required for weapons-grade uranium takes shockingly little additional effort. The hardest part of the work is already done at the low enrichment stages. The exact same rotors, piping, and cascades used to light a city
can produce the fissile core of a nuclear weapon. They don't need new technology, they just need to feed the material back into the cascade and run the machines longer. This breakout potential is why international monitors from the IAEA have to constantly inspect civilian feed systems and frequency changers. They have to continuously verify that the gas isn't being cycled back through for rogue enrichment. The nuclear fuel cycle creates a paradox. The same machinery that generates clean power also grants the capacity for total destruction. A nation cannot possess the technology to harness the atom for peace without inherently holding the machinery to weaponize it.